Hello dear learners, welcome to the online course on electricity and electrical wiring. This is the third lecture of module 7 on electrical house wiring. In this lecture, we will explore the various connection schemes used in house wiring, various tests performed in new installations and different systems of wiring used. So by the end of this lecture, you should be able to understand the different types of connections used in house wiring, perform the various tests required in a new installation, identify and select the appropriate wiring for given case. With these objectives in mind, let us begin the lecture. So in our previous lecture, we learned that all single phase devices require a phase and a neutral connection for their working. Also, we need switches for their control. Now the question arises, how do we make these connections? Electrical connections can be broadly classified into two categories. Series connection, where the devices are connected end-to-end in a single loop. Parallel connection, where devices are connected across the same voltage source. Each type of connection has its own applications and advantages. Now, let's talk about the series connection first. In a series connection, electrical devices are linked end-to-end, creating one single path for the current to flow. One key characteristic of a series connection is that individual control of each device is not possible. Since all devices are part of the same circuit, turning the switch on or off will control all these devices simultaneously. As you can see, when the switch is turned on, all the devices will turn on, and when the switch is turned off, all the devices will turn off. In a series connection, the supply voltage is divided among all the connected devices. Although this setup is simple, yet it is not ideal for most household appliances. This is because of the lower voltage per device, the lack of individual control, and the dependency on all devices functioning correctly. Series connections are therefore mostly used for decorative lighting during festivals or similar occasions. In this case, a large number of lower voltage rated lamps are connected in series. Each series string is in turn controlled by either a manual switch or a power electronic switch. Now, let us talk about the parallel connection. In a parallel connection, all devices are directly connected to the supply voltage. Unlike a series connection, where the voltage gets divided, here the voltage is going to remain the same across each device. One key advantage of parallel connection is that each device can be controlled individually. In a parallel circuit, the total current is divided among the devices based on their respective impedances. You see, parallel connections are widely used in household, wiring and industrial setups. This is primarily because all devices are supplied with the same voltage, each device can be controlled independently, and if one device fails, the rest continue to function normally. Okay, now let's explore the parallel connection in more details. As per IS code, the live wire must be connected to the switch. The other end of the switch should be connected to the load, while the neutral must be connected to the load. If you look at the circuit, each of these lines in the diagram physically represents a cable. Now as you can see, there are certain places where we need to make multiple joints. So how do we do this? One option is to slice the cable at these junctions to expose the conductor part. Then we make the joints by connecting the cables and finally wrap them with insulation tape. Although this is a feasible solution, it has several disadvantages. There is the possibility of local heating at these points, which could lead to fire. Additionally, loose connections may occur and finding faults could be very challenging if there are many such joints. To make the connections safer and more efficient, two types of connection systems are commonly employed: the joint box system and the looping in system. Now, let's understand the joint box system with the help of an example. In this example, there are 4 loads and these are to be controlled from 2 different switchboards. Regarding the connection, the main phase wire from the distribution board needs to be supplied to the 2 switchboards. As shown in the figure, a T-joint is made near the first switchboard at the main wire. From here, a phase wire branches off from the main phase wire to the first switchboard. The live wire is then connected to the first switch, and from the first switch it is extended to the rest of the switches in the first switchboard. Similarly, another branch is taken from the main phase wire at this T-joint to the second switchboard, where it is further connected to the switches of the second switchboard. After this, the other end of the switches are connected to the respective loads. The neutral wire from the distribution board forms a T-joint at each load from where a branch of the neutral wire is connected to the load. In the joint box system, these joints are made inside special joint boxes. These boxes have the necessary arrangement to make proper connections. Wherever there is a need for these joints, these boxes are installed. This method is better than slicing the cables for joints in many ways. However, this system still has some drawbacks. While the risk is lower, there's always the possibility of faults in these joints, often caused by overheating or loose contact. If the number of joint boxes is large, locating these faults can become difficult and tedious. Now, a better practice is to avoid using these joint boxes altogether. This is done by employing the looping in system of wiring. In this system, the main phase wire from the distribution board is taken to the nearest switchboard. Here, the phase wire is connected to all the switches. To provide power to the second switchboard, a connection is taken from the phase wire connected to any of the switches in the first switchboard. This connection is then extended to the second switchboard, where it is connected to a switch. The phase connection is extended to all the other switches of the second switchboard. This process is repeated for all the switchboards within a particular subcircuit. The other terminals of the switches are connected to their respective loads. The neutral wire from the distribution board is connected to the remaining terminal of a load. To minimize the length of cable, this load is typically the nearest one to the distribution board. From the first load, the neutral connection is extended to the next nearest load. This process is repeated until all the loads receive a neutral connection. The main advantage of the looping in system is that no tap-offs are made directly from the main wires, and as a result, no joint boxes are required. However, the length of wire needed in the looping in system is longer compared to the joint box system. Let's now look at an example of the looping in system. Let's start with the phase connection first. The phase wire from the distribution board is connected to switch number 1. From here, it is extended to switch number 2 and switch number 3. The load terminal of switch 1 is connected to the lamp. The load terminal of switch 2 is connected to the fan regulator, and other terminal of the fan regulator is connected to the fan. The load terminal of switch 3 is connected to the phase terminal of the 6 ampere socket. Now for the neutral connection, the neutral wire from the DB box is connected to the neutral terminal of the 6 ampere socket. For this example, we are assuming that socket is the nearest load from the DB. From the 6 ampere socket, the neutral connection is extended to the lamp. From the lamp, it is further extended to the ceiling fan. This completes the neutral connection for all the loads. Finally, since there is a socket outlet, an earth wire is taken from the distribution board and connected to the earth terminal of the socket. So far, we have seen how to control one device from one location. Now let's discuss the connection where we may need to control one device from two locations. This type of connection is commonly used in staircase lighting, corridors, etc. In staircase lighting, it's necessary for a person going up the stairs to be able to switch on the light and after reaching the top, switch it off. Similar situation arises when climbing down. For this type of connection, two-way switches are required. Unlike single-way switches, the two-way switches have three terminals. One is the common terminal and the other two are the line terminals. When the switch is in the upward position, the common terminal connects to the line terminal L1. In the downward position, the common terminal connects to the line terminal L2. To control the lamp from two locations, we need to install two number of these two-way switches at these particular locations. The connections are made as follows. The phase wire is first connected to the common terminal of switch number 1. Then L1 terminal of switch 1 is connected to L1 terminal of switch 2. Then L2 terminal of switch 1 is connected to L2 terminal of switch 2. The common terminal of switch 2 is then connected to the lamp. The neutral wire is then connected to the other terminal of the lamp. This completes the circuit. Now, for the operation, the lamp will be on under two conditions. First, if both the switches are in the upward position, connecting L1 terminal to the common terminal, and second, if both the switches are in the downward position, when the common terminal is connected to the L2 terminal in both the switches. If one of the switch is in the upward position and the other is in the downward position, the lamp will be off. So this completes our discussion on electrical wiring connections commonly practiced in house wiring. So I hope you will now be able to design house wiring for any given situation. Now let us assume that you have done the design and after that completed the house wiring installation. So what's next? You see, before any new installation is put to service, a number of tests must be carried. These tests are essential to ensure that there are no defects that could cause danger to human life or property. According to the IS code 732, a number of tests should be conducted before a new electrical installation is put into service. Let's now discuss these tests one by one. The first test that we are going to discuss is the insulation test between conductors and earth. This test is conducted to check if cables used in the wiring are sufficiently sound and there is no leakage current. To conduct this test, a Megger instrument is required. The voltage supplied for the test should be a DC voltage, and it must be at least twice the working voltage of the circuit under normal operations. For example, if the working voltage is 250 volts, the Megger should have a rating of at least 500 volts. Now, let's go through the step-by-step procedure for conducting the insulation test between conductors and earth. First, the output terminals of the energy meter must be disconnected from the main switch. Next, turn on all the switches. Then connect one terminal of the Megger to earth and the other terminal to the phase and neutral conductors together. Now operate the Megger and measure the insulation resistance. The test connection discussed is shown in this figure. As you can see, the supply is disconnected from the main switch. The phase and the neutral from the main switch are connected to one terminal of the Megger. The other terminal of the Megger is connected to the earth. Finally, the switches are in the on position. After the test, if the Megger indicates 0 or a very low reading, it indicates a low resistance path. A low resistance path between the earth and the conductors, and the faulty condition must be identified and immediately removed. The reading of the Megger should not be less than 50 divided by the total number of outlets. Here, each switch, socket, holders, etc. are considered as outlets. In general, a resistance of 1 mega ohm may be considered sufficient. The next test that we are going to discuss is the insulation test between conductors. Electrical insulation testing between conductors is crucial to ensure that there is no unwanted current leakage between conductors. The objective of this test is to check the insulation between the line and the neutral in case of a single phase installation. In a 3-phase 4-wire system, the test must be conducted to check the insulation between all possible conductor pairs. Another objective of this test is to locate short circuits, if any, in the complete installation. A Megger is required to conduct this particular test. To begin the insulation test, first disconnect the output terminals of the energy meter from the main switch. Then ensure that all switches, breakers and fuses are turned on. After this, remove all devices from the circuit. Next, connect one terminal of the Megger to the phase conductor and the other terminal to the neutral conductor. Operate the Megger and measure the insulation resistance. In case of 3-phase 4-wire system, perform this test between all possible pairs of conductors. The figure shows the connection for the test. As you can see, the supply is disconnected from the main switch. The phase and the neutral conductors from the main switch are connected to the two terminals of the Megger. The switches are put in the on position. Finally, the loads are disconnected from the circuit. After this test, if the Megger shows 0 readings, it indicates a short circuit in the wiring. This needs immediate attention. For a proper and safe installation, the insulation resistance should be greater than 1 mega ohm. Now, let us discuss about the earth continuity test. The earth continuity test in an electrical installation is performed to verify that all metallic parts intended to be earthed have a low resistance path to the earth. This ensures a safe route for the fault currents, preventing any potential hazards. If there is a break in the earth connection, fault current may pass through a person, increasing the risk of electric shock. To conduct this test, a megger is required. Now, let's discuss the procedure to conduct the earth continuity test. First, disconnect the output terminals of the energy meter from the main switch. Next, connect one terminal of the megger to the metal part of the installation. Then, connect the other terminal of the megger to the earth. Now, operate the megger and measure the insulation resistance. If the reading is 0, it indicates proper earth continuity, meaning the connection is intact. However, if the reading is high, it suggests a discontinuity in the earth connection. This needs to be checked and corrected to ensure electrical safety. The last test that we are going to perform is the polarity test of switches. The aim of this test is to verify that all switches are properly connected to the live terminals. To perform this test, we will need a test lamp with 2 long leads. The test lamp will help determine if the switches are correctly wired to the live supply, preventing any potential electrical hazards. Now let's go through the procedure to check if the switches are correctly installed on the live terminals. First, disconnect all the appliances, lamps and any other connected devices from the circuit. Next, put on all the breakers and the fuses in the circuit. Then turn on all the switches in the installation. Now switch on the main supply. Then take the test lamp and connect one of its leads to the earth. Then use the other lead to test each switch one by one by touching the terminals. If the lamp lights up when testing a switch terminal, it indicates that the switch is correctly installed on the live wire. If the lamp does not light up, it means the switch is installed on the neutral wire instead of the live wire, which is incorrect and needs to be corrected. Okay, so this completes our discussion on the various tests that need to be performed before a new installation is brought to service. Now, let us discuss the different types of wiring systems used in electrical installations. The main types of wiring systems include cleat wiring, batten wiring, conduit wiring, and casing capping wiring. Cleat wiring is one of the simplest and oldest wiring systems. It consists of insulated wires that are supported by porcelain, plastic or wooden cleats, which are fixed on the walls or ceilings at regular intervals. This type of wiring is temporary and is mostly used in construction sites, events and any such temporary installations. One of the main advantages of cleat wiring is that it is cost effective and easy to install. However, it lacks durability and is not suitable for permanent electrical installations. Batten wiring is a simple wiring system where insulated wires are laid over a wooden batten and held in place using clips or brass pins. The wooden batten is securely fixed to the walls or ceilings using screws. This type of wiring is commonly used for indoor applications where mechanical protection is not a major concern. Batten wiring is easy to install, cost effective, and provides a neat appearance. However, it is not suitable for damp or outdoor conditions, as the wooden battens may deteriorate over time. Conduit wiring is a more advanced and secure wiring system where electrical wires are enclosed in PVC or metal conduits. These conduits can be installed on the surface of walls, in which case it will be called as surface conduit wiring, or hidden inside walls. In this case it will be called as concealed conduit wiring or recessed wiring. This type of wiring provides excellent protection against mechanical damage, moisture, and fire hazards, making it suitable for industrial, commercial, and residential buildings. Although conduit wiring is more expensive and requires skilled installation, it offers a longer lifespan and ensures maximum safety. In casing capping wiring, wires are placed inside a rectangular PVC or wooden casing, which is fixed to the walls or the ceilings. The casing is then covered with a capping to protect the wires from external damage. This type of wiring provides good insulation and neat appearance, making it a popular choice for residential and commercial applications. Casing capping wiring is affordable, easy to maintain, and protects the wires from dust and moisture. However, it is not as durable as the conduit wiring and may not be suitable for heavy-duty applications. So dear learners, it is now time for a self-check of what we have learned so far. Please pause the lecture and attempt the following questions. So dear learners, in this lecture we started with a discussion on different types of connection for house wiring. We have seen two special types of parallel connection normally used for house wiring. We then understood the various tests that need to be performed before putting a new installation in service. Finally, we have discussed the different systems of wiring. In the next lecture, we will discuss the different tools used in house wiring. I hope the information shared in this video has helped you further enhance your understanding of house wiring. Thank you.